Hello, everyone. My name is Yidong Zhao. I'm a PhD student from the University of Hong Kong. In this talk, I will present stabilized material point methods for large deformation in fluid-infiltrated porous materials. I will start from the background and give the motivation. Large deformation problems are everywhere in the world. Two typical examples are landslide and wave failure. These failures often brings huge damage on infrastructure. Also, in landslides, many people may be killed. Among them, the pore water pressure take a very important role in the development of failures. Also, both quasi-static and dynamic conditions are common. Our goal is to understand these failures numerically. So in order to consider pore pressure, the coupled poromechanics is necessary. It is consisted of two balance equations. One is the linear momentum balance, the other is the mass balance. They are fully coupled together in displacement-related quantities and pressure. Here I use yellow color to represent displacement-related quantities, while I use blue color to represent pressure. In order to consider a large deformation, material point method or MPM is an ideal choice. This method has recently widely used in a variety of geotechnical problems involving large deformation. The following figure is a calculation procedure for the MPM. So in the first step, we map the information from the particle to the background grids. In the second step, we solve the Goldman equation on background grids. In the third step, we map back the information to the particles, and in the fourth step, we convect the particles. Among them, the second step is actually exactly the same as finite element method. So MPM can be understood as a modification of FEM with movable quadratures. However, the coupled MPM have some challenges. Because most geotechnical problems involve undrained condition under small permeability or time step. Under this constraint condition, it should satisfy a stability condition. However, standard MPM using linear basis functions for displacement and pressure is not stable. Here, standard MPM means we use linear interpolations for both displacement-related quantities and pressure. The violation of this stability will make the problem ill-posed, and it will result in a checkerboard oscillation in a pressure field, here I show in this red region. There are some existing stabilization strategies for coupled MPM. One is the fractional step method. This method splits the velocity increment into two parts. Although it works well for dynamical problems, however, there are some limitations. The first is that the time step algorithm need to be changed a lot. Also, some additional computational effort is needed to solve for the intermediate terms. And additionally, it does not work for quasi-static problems. The second method is a reduced integration. It calculates the pressure gradient at the background grid center. However, the limitation is that this method is actually not completely stable. So it may show some oscillation in some certain conditions. So far, the question is whether there is an easy way to stabilize the problem under both quasi-static and dynamic conditions. Because there are many similarities between MPM and FEM. Let's have a look at a stabilization method for FEM. This method is called polynomial pressure projection, or PPP. It's originally developed for Stokes flow and later extended to poromechanics. In the right two figures, the unstabilized FEM shows heavy oscillation in pressure field, while stabilized FEM gives a smooth pressure field. Now, let's have a look at the mechanism of this method. So this is the original Lie matrix equation for a coupled poromechanical system. However, under undrained condition, this C block will nearly becomes zero. So this serves as a constraint. Under this constraint, a stability condition should be specified for the discretized system. Unfortunately, if we interpolate the displacement and pressure of the same order, it does not satisfy this stability condition. However, it does satisfy a weaker stability condition. Here I show here. Compared with these two conditions, we can immediately say that these quantities quantifies the deficiency of the equal order interpolations. So the mechanism of PPP is to penalize this deficiency. An additional term is added to the mass balance equation. Correspondingly, there appears additional C block here. So this is the mechanism of the PPP method. Notice that this is very easy to implement because there is no need to modify the time-step algorithm. Additionally, it works well in large deformation quasi-static conditions as shown by Sun et al., and also it works well in large deformation dynamic conditions as shown by Monfort et al. So we think whether it's possible to extend the PPP for MPM. In order to extend for MPM, we need to do some modifications. Let's now have a look at the stabilization term more closely. So it consists of three parts. The first part is a stabilization parameter. The second part is an element-wise average term. And the third part is a time derivative. Because here I use red color to represent a material point particle. This particle may influence multiple background grids, so we need to modify this element-wise average term. We borrow the idea from Kuhnbull et al. To use modified shape functions in MPM, which is originally designed for getting blocking-free deformation gradient. After using this modified shape function, we can get an average term. So we can calculate this stabilization term for MPM. Then we can extend the PPP method for MPM. Now I will use two numerical examples to show the performance of the stabilized MPM. The first example is a saturated porous ground under harmonic loading. This is a dynamic problem. This example serves as a verification. From the movie, we can see that the unstabilized MPN shows heavy oscillation in pressure field, while stabilized MPN gives very smooth pressure field. We compare our results with the numerical solution from the stabilized FEM. Here is shown in black dashed line. Our stabilized MPN corresponds very well with the correct solution, so it verifies the stabilized MPN. Additionally, because there are some different suggestions for the stabilization parameters, so we do some analysis on different choices. Our results show that it is insensitive to these two suggested stabilization parameters. So there is no parameter tuning is necessary. The second example is a long-term consolidation. This saturated porous domain will consolidate under its self-weight. Notice that the domain will initially deform in a strict undrained condition. Also notice that the whole consolidation process lasts several months, so an unconditionally stable fully implicit scheme is required. This is a quasi-static problem. Again, because instability makes the problem yield-post, so our unstabilized MPM does not converge just after the gravity is added, while stabilized MPM gives a smooth pressure field during the whole process of consolidation. To summarize, we developed the first fully implicit stabilized coupled MPN for large deformation quasi-static and dynamic problems. This method is easy to implement without any change of the time-step algorithm. And additionally, parameter tuning is not necessary. This work has been published on CMME, so we recommend interested readers to read our paper on more detailed discussions. That's all for this presentation. Thank you.